All right, let's jump in. So last time we talked about balancing redox reactions, and so that's required before you can calculate cell potentials. And so today we're going to talk about galvanic cells and their voltages, which is the basis of pretty much every battery that we have. So we'll learn a lot about batteries, at least in theory today, and then we'll on Friday get into non-equilibrium situations, actual batteries, and talk about corrosion and electroplating, so other applications of electrochemistry. So let's talk about this idea of a voltaic cell. You know, in a spontaneous redox reaction, these electrons are transferred from one reactant to another, and that's why we call them redox reactions. There's a reduction step and an oxidation step. And if we can get those electrons to go through a device using electrodes like this, then we can actually get work out of the system. So in this case, just the potential of this copper electrode in contact with the copper ions and the zinc electrode in contact with the zinc ions, when we make an electrical connection between these two, there's a push on the electrons, just because the substances are different. So every one of these substances has a different activity in how it pushes on the electrons. And in this case, we can get like 1.1 volts out of zinc and copper with one molar solutions of zinc ions and copper ions. This little plug in the middle is just to keep the ions separate so that you can keep this to be 1 molar copper and this to be 1 molar zinc. But you do need an electrical connection, and so the ions have to transfer through this little spot. So in every circuit, we'll see this next, we have this thing called a voltaic cell where you actually have to conduct the ions and the electrons. So let's look at a more detailed picture of this voltaic cell. So here's the copper electrode over here, okay, and it's in contact with a 1 molar solution of copper nitrate. It doesn't really matter what the anion is. It's just really the cation in contact with its metal. And then over here we have zinc cations in contact with zinc metal, and then nitrate. And so when we hook this electrical circuit up, there's actually a force, a push on those electrons, and that's what a volt is. It's an electromotive force. It's how hard those electrons are being pushed. And if we put a meter on there that can measure that push, in this particular setup, we get 1.1 volts, okay? And you know the different batteries have different voltages and so on. Your car battery is a 12-volt system. Your, AA batteries and so on, those are 1.5 volts. And so this is, again, this different push power comes from different chemistry and chemical reactions. So if you get current flow and the electrons go this direction, you also have to have ion flow. And so you have to have these ions flowing through an electrolyte. This particular thing, if you see it in the lab, this is called a salt bridge. Okay. And in this case, the salt is sodium nitrate. So they pack this thing with sodium nitrate and get it wet, and so some of those sodium and nitrate ions dissolve in that solution. And so when these copper ions played out onto the copper electrode, because the electrons come in here, so we have electrons flowing in and they attach to the copper element or copper ion and make copper solid. And so there's a flow or essentially there's a loss of cations in this beaker. And if we didn't have this salt bridge, then you might get a small burst of current and then everything would stop. So this salt bridge allows the ions to also reset that imbalance. So 2 of these sodium ions will come out. I think that is sodium. For every copper that plates out. So the copper will plate out on this cathode and 2 sodium ions will come into that beaker so that we don't build up a positive charge on one beaker and a negative charge on the other. Then on this side, the zinc metal is becoming zinc ions in solution, okay? And where did the electrons go? The electrons went up through the circuit. So we have cations being generated in here, and for every zinc cation that's generated, 2 of these nitrates come out of the salt bridge. And so they're coming into that solution to keep the charge balanced. And so the nitrates are moving in a sort of a counter, let's see, I guess clockwise, they're going through the salt bridge in this direction, and the cations are going in the opposite direction. And so electron flow is being shown here, and then positive flow, if you want to think of it that way, there's really not positive flow through the wire. There's just electron flow, but it looks, you could look at it and say, well, it looks like positive flow is going the other direction. And before they knew about electrons, before they knew about cations and anions really, they knew that they could charge up rods, they could charge up things. And in the early experiments with electricity, they defined current as positive, the flow of positive charges. And so the definition of current is sort of backwards to what really happens. And so the current is if you know, in mathematically, the current is flowing this direction. This positive flow is actually the current direction. So current's flowing this direction. But it's really electrons that are flowing. So how does this work in terms of our power system? They have a generator, and it is generating this voltage by stuffing electrons down into the earth. And so they're making the wires really, really positive. So those power lines that you see are really positively charged by thousands of volts, especially the transmission lines. Those big transmission lines are like 380,000 volts each wire. And we bring those to our house, we cut the voltage down, and into our house comes about like 240 volts, and then that's broken into a couple of lines of 110 volts, 110 volts. And then we plug in our equipment, and it's connected to ground. And so electrons are flowing out of the ground through our equipment back onto this positive line to be sucked out at the power plant. So that's actually what's happening. The electrons are flowing back to the power plant. But that doesn't kind of seem right. The power plant's giving current to our house. So it's the positive flow that we defined as current. So current's flowing from the power plant to our house, but it's in reality what's moving is the electrons. The electrons are going through from the ground, through our equipment, and then out to the power lines. So now in terms of oxidation and reduction, oxidation occurs at the anode. So this is the anode, the zinc anode here. And it's going from zinc metal to zinc cation. So oxidation is loss of electrons. And so when it goes from zinc solid to zinc 2+, we've lost 2 electrons. And then reduction takes place at the cathode. So over here's the copper cathode, and the copper 2+ is gaining 2 electrons and becoming copper solid. So that's reduction is gain. And so you remember that whole thing from oil rig from last time. Okay, so this is a galvanic cell, a voltaic cell. Okay. So these standard cell potentials, we could find them through this equation here, this E cell, and it's the reduction potential at the cathode minus the reduction potential at the anode. And the reason we have reduction on both of these is because that's how the table is listed. So if you look at the table on your homework, every one of those reactions is listed as a reduction. But this piece right here is actually the oxidation potential. So when you take into account that minus sign, so the opposite sign of the reduction potential is the oxidation potential. And oxidation takes place at the anode, reduction takes place at the cathode. So whatever reaction you have at the anode, you flip the reaction and flip the sign on the reduction potential number, and then you can add them together. And so this is a nice trick to remember which one contains the oxidation and the reduction. So I came up with this little trick, and like it says, I'm very proud of it, okay? Because we're dealing with electrochemical circuits, and so we have, think of it as 2 beakers with a salt bridge in between, and which one, the electrodes go down into the beakers. And so which one is associated with reduction and oxidation? There's only one way to build it. Reduction is the only one that has only one of those that has a C in it. So you can put cathode on reduction, and that cathode goes down into solution. So this sort of represents the cathode, and this reinforces that reduction takes place at the cathode. Notice I can't put the word cathode anywhere on the oxidation, okay? Whereas oxidation has an A in it, and you could put anode on the oxidation word. So this way you'll never forget that oxidation and the anode go together, and reduction and the cathode go together. Okay. So I talked about the standard reduction potentials, and we have these tables, some in your homework, some here in the notes. And we can look at this table, and whenever they're sorted high to low, right? So this is less negative, so this is a high to low, being very negative down here. Then clockwise pairings in this table are spontaneous. So we could take this reaction written in the forward direction and combine it with any one of the ones below it written in the opposite direction. So if we take this reaction and we swap the arrow, then zinc becomes a reactant and the zinc 2+ becomes a product. So we have this one in the forward direction with the reduction potential of 0. So that's the definition of our reduction potential, relative values in our table. And we write the zinc one backwards. So you see how this is backwards? Is zinc solid on the left. So you go to the reduction potential table. If it's sorted high to low, then any clockwise pairing, do you see how what I'm saying about that? That's just, this goes this way, and then it pulls this reaction backwards. Okay, so that's a clockwise pairing of two reactions. And so that means that this is a reactant, and these are reactants. So we put those together on the left side of our arrow, and then we put the products together on the right side of the arrow, and then we swap that reduction potential for the reaction that we switched. And so we have a minus negative 76. And so then we add everything down. This is nice because the electrons match. So they cancel each other out. And we have the reactants giving the products here. And this is the cell potential for that reaction. We could have done the same thing for iron. So we could couple acid protons with iron metal and produce hydrogen gas and iron cations. And that would be spontaneous as well. So because this is a positive number, so it would proceed without any outside influence. This is actually, think about this. This is kind of dangerous, right? This tells us if we have a zinc container or even like a galvanized metal container, which is it's like an iron coated in zinc, and we put acid in that container, it's going to dissolve the metal and it's going to produce hydrogen gas, which is a flammable gas. So we really don't want to store acids in metal containers that have metals that are below hydrogen in this reaction here. So this reaction right here will produce hydrogen gas with nickel, with iron, with zinc, with any of these metals that's below it. And so that's something that we want to avoid. So let's talk about the electrical potential. Let's put some numbers on this. I'll put this equation in the corner of your notes, like on several slides, just to kind of emphasize it, that we're now able to couple delta G with the electrical potential. And so this electrical potential depends upon delta G. It's how hard the reaction is trying to go in a spontaneous manner. Can I get you to close that door? And so if you look up here, there's this minus sign. So if the delta G is really strongly negative, then we're going to have a really positive cell potential. Okay, so positive cell potentials are spontaneous. This F is a new constant for you. It's Faraday's constant. It's the number of Coulombic charges you have in a mole but it's also over here, it's the joules per mole for every volt that you have. And so it's a conversion factor. It converts, you could write it like this, joules per mole per volt. Okay, so that would be Faraday's constant. So here it is in the denominator, so it cancels the joules per mole of Gibbs free energy and gives you volts on top. Okay, so let's look at this reaction. Remember, we had the general Gibbs energy reaction and the standard Gibbs energy and this RT ln Q. We use Q because we're not at equilibrium. So if we make this substitution of minus NFE for delta G, then we have this here. Okay. And we do the same thing here with the little superscript 0 to show the standard conditions. And then we have RT ln Q. If we divide everything by minus NF, then this sign becomes negative, and we end up with an NF under that RT. So that's how we get to the next line. So we have the cell potential is equal to the standard cell potential minus this correction factor that depends upon our equilibrium, or I mean our non-equilibrium reaction quotient. So we're using Q because we're not at equilibrium. And this is actually called the Nernst equation, and it helps us come up with this cell potential of any situation when we have different concentrations and different temperatures and so on. But it's not typically written in natural log form. So let's figure out how we get to the base 10 log form of the Nernst equation. And we'll do that in the next slide. This is what we did for the Gibbs energy. You should recognize this from maybe 3 lectures ago. We had this is at equilibrium. We set it equal to 0, and Q became K. And then we rearranged. So we found this relationship between the standard Gibbs energy value and the equilibrium constant expression. And then you could rearrange this to solve for the equilibrium constant expression based upon the standard Gibbs energy. So this is review. But let's take this part right here and branch off and put in that minus NFE for G. Okay? So instead of delta G 0, we have that minus NFE at standard conditions. And since we're here at equilibrium, we've got this equilibrium constant. Okay, we can divide both sides by negative NF. And so in this case, so then the negative signs cancel. And we have this cell potential, the standard cell potential is equal to RT NF times the natural log of the equilibrium constant. So that's pretty cool. Right there, we could take the equilibrium constant if we know K, and we know how many electrons are in the balanced equation, the redox reaction equation, we could calculate what the standard cell potential would be. But more frequently, if we have a redox reaction, we actually measure the cell potential, and that's how we get the equilibrium constant. So we measure this. And then we get K. So that's how equilibrium constants are found for electrochemical reactions. It's fantastic. And then we would use K to get to delta G. We could use delta G to calculate all kinds of things. So then let's convert that Nernst equation from the natural log version to the log base 10 version. So here we started again with that delta G value. We could make those substitutions, and we get to this natural log version of the Nernst equation. Okay, and this is again a standard temperature, and so we can simplify this, and so it would always be RT over F. These three are constants, and so we can make life simple for us and just calculate that value here. And so then we end up with this log base value, natural log base value, or base E value for the Nernst equation. And that's where this number comes from. You'll see this in the book and other places, and you'll think, gee, that's a strange number, 0.02569. But that's RT over F. And then if we wanted to convert from the natural log to the common base 10 version, then the natural log of Q is this natural log of 10 times the log base 10 of Q. So that 2.303 times this 0.025 gives us this more frequently seen version of the Nernst equation. And this will be given on the test, you know, when we're asking for these things, because I don't want you to mess this problem up just because you can't remember 0.05917. That's kind of a strange thing. And it's not as, like, I'll make you memorize the gas constant, you know, but they use that one a whole lot more than you use this one. Okay, so I'll go ahead and give you this equation to use, just so you don't mess that up. Plus, you still have to know how many electrons are transferred in the balanced redox reaction. So there's still some work to be done with this equation, but I'll give it to you on the test so that you'll know that you're not at least messing up the equation. It'll be the Wednesday after Thanksgiving. Okay, so instead of giving you, I don't like giving you a test right when you come back from a long break, and so we'll have a review on that Monday, and then the next exam will be that Wednesday. And then the final will be the following Monday. And so start studying now. Start pulling down the homeworks and going through the, you know, the online, the answers are on Blackboard. So just start working through the different parts. It really is, I mean, education in general, it really is like lifting weights. You know, if you've got a wrestling match in 3 weeks on a Saturday, you can't cram all your weightlifting the Friday before. That doesn't make any sense. Okay, you've got to build that muscle memory in your brain. It's not a muscle, but you know what I'm talking about. Like when you see a particular type of question, you need to know what you're doing instead of trying to figure out, oh gosh, this was 6 months ago, what do I do? You know, that you're not going to be able to cram all of that information in your head. So start now, start refreshing your memory. So let's use the Nernst equation. So what's the potential of an aluminum manganese cell where these are not at standard concentration? So the aluminum concentration is 0.001 molar and the manganese is 2 molar. So standard concentrations, you know, this little guy right here would be 1 molar for everything. And so the Nernst equation helps us determine what the cell potential would be when we're not at standard conditions. So this is the Nernst equation. We look at this reaction. We've got to make up Q. And so Q incorporates all of the things that are aqueous or gases. So that goes in there, and then it's squared. So for redox reactions, we have a lot of crazy exponents. Things are squared. Sometimes they're to the 8th power and so on, like if you have 8 protons. And then it's divided by the reactants. So the manganese is here, and it's cubed. And we've got our concentration. So we know what the aluminum is. It's 0.001, and the manganese is 2. So we put those in. And this is the standard cell potential. So this 0.48, you know, is this thing. And so what we see, and in a second we'll determine what we expect, right? But we've got Q. Q is, you know, much less than 1. It's 0.001 squared divided by 2 cubed. Okay, so this is a much less than 1. That's going to make a negative log, but then we have a negative sign over here in front. So it makes a positive correction. So all of this piece right here is at the 0.07. So the concentrations, the electrons, and so on that are transferred all correct this voltage and add 0.07 more volts to it. So this cell would actually produce 0.55 volts. Okay. Now, would we expect that? If we look at this, think about Le Chatelier's principle. This is the voltage when everything is 1 molar. Okay? And our products are much less than 1 molar. Our products are 0.01. So we have a smaller amount of products than the standard. And our reactants are greater than 1. So we have more reactants than the standard. You see how Le Chatelier's principle would make this reaction want to go forward more? Because we have less products than the standard situation and more reactants than the standard situation. So it's pushing harder. And so it should have a higher voltage. And it does. It has a 0.55 volts as opposed to 0.48. Okay. And so this just take note, as this galvanic cell reaches equilibrium, this cell will drop. So as these values move closer to their equilibrium values, or even closer to the they'll move towards the standard values, all right, where you've got 1 molar of this and 1 molar of that, and then this correction will be 0, and then it'll start going down, like it'll start approaching 0 as you start getting more and more products and less reactants, okay? Then that's going to be at the log of a number that's greater than 1, and that's going to be a positive log. And so this negative sign is going to be retained, and it's going to start chipping away at our voltage, and our voltage is going to drop. So when the system reaches equilibrium, the cell potential is 0. So that's why a battery goes dead. As it reaches equilibrium, the voltage, how hard it's pushing on those electrons, just dwindles down to nothing. It's not pushing electrons anymore because it's at equilibrium. Okay. If you wanted a really, like a scam business, okay, you could sell ultra-safe pre-equilibrated batteries. Doesn't that sound great? Pre-equilibrated batteries? This is nothing more than a dead battery. Okay, but they're really safe, right? They couldn't cause a fire because they don't push any electrons. So I'm not advising you to do that, but that would be a definite scam. They're ultra safe, okay, and everybody's all about safety. Okay, so let's think about this idea of dependence on concentration. So at the standard conditions, all the concentrations are 1 molar. If they're not 1 molar, then you can figure out, using Le Chatelier's principle, what should happen, like predict that the cell potential would be higher or lower. Okay, so in this case, that whenever the aluminum was at 2 molar and if manganese is at 1 molar, what would we predict, right? So I've got too many products, and so it's going to want to push the reaction backwards, and so the cell potential would be less than the standard. This little degree symbol is really important, right? Otherwise, that doesn't make sense if you don't recognize that little degree symbol or superscript. This is the cell. This is the potential of the actual battery. This is the standard situation. And it's fixed. It's right here at 0.48. Okay. And this is saying if my concentrations are not at the standard concentrations, I should be able to predict whether the cell potential will be less than the standard or greater than the standard. And in this case, I've got too many products. That's a product. And so my cell potential will be less than the standard because I've got too many products. Okay. What about this one? If the manganese is at 2, I've got too many reactants. And so that'll push the reaction forward, so my cell potential will be higher. It'll be more spontaneous. It'll be pushing harder to go forward. And of course, they're not at equilibrium, so we're using Q, not K. Q is trying to get to K. Okay. Any questions on this? This is something that should be easy. When I was talking about fundamental questions, this would be one of those fundamental questions. The standard concentrations for all aqueous species is 1 molar. That's easy. So if it's not 1 molar, you're not at the standard setup. And so then you could predict whether the cell would be higher voltage or a lower voltage. Okay, this is kind of fun. The Nernst equation implies that a cell could be created that has the same substance at both electrodes. So in this case, this is a really weird cell. It's got a nickel anode and a nickel cathode, and yet it's giving a voltage. It's not much, but it's 0.08 volts, or really closer to 0.09. Why is that? Well, look at the concentrations. This one is 1 times 10 to the minus 3 molar, and this one is 1 molar. So that's enough to give this a voltage, enough for it to push on the electrons. So what would happen in this case? Well, I don't have very much nickel here, and so some of this nickel would go into solution to make nickel 2+. okay? Where did those electrons go? Those electrons went this way, okay? This has too much nickel, 2+ in it. And so it's gonna decrease its concentration by plating out and using those electrons. So these electrons come in, they join with the nickel 2+, make nickel cation. So this electrode will grow. And this one will shrink. As these things come to equilibrium, which will be the same concentration in each flask. Okay, and so over here we have 0 voltage when they're both the same concentration. And so you could set up a battery with just a metal and its salt. It's a concentration cell. You can just put those in and just have pure water on one side and the concentrated amount of the salt on the other, and you'll get a voltage across that. So,
what do you mean by one of the shrinking?
The actual electrode, because this is nickel 2+ plating out to become nickel solid, and so it'll actually grow. Yeah, and so you'll see more nickel on that electrode at the end. So this one right here would be kind of fuzzy with nickel because it kind of grows around the outside and makes little needles and stuff. And so that would be, and it would be kind of hard, like it wouldn't be shiny because these little structures are, sometimes they appear really dark in color because they absorb light. They don't reflect because it's not a smooth surface. And so it will look like kind of like hair growing on that electrode. And this one will maybe even get eroded. Like it'll shrink and get chewed up. And so you'll see some of this looks chewed. If you have a dog, you know what I'm talking about. Yeah, and so it's just nature hates that, right? And so you put these in contact with each other and electrons are trying to fix it. So the ions will also move too. We lose cations, the salt bridge, so this sodium ions or whatever will come in here. And if it's like a nitrate, sodium nitrate, then nitrate ions will come in here. So you need that salt bridge to connect these, but you just can't let the solutions mix, right? If you just put a path between these, a pipe between these, then they're just going to diffuse into each other, and you won't get any electricity out. But because you don't let them mix, then you're forcing the electrons to go through the wire, and you're forcing the ions to go through this salt bridge. And so it's the salt bridge is not talked about a lot, but it's really critical. This sort of is a barrier. It's a barrier to keep these solutions from mixing. So we're just making the ions go in to balance out the charges, but we're not letting the nickel flow through that. I mean, some will flow, maybe some of this nickel gets in here, but it's not going to go very far, right? So there might be a little nickel in here, nickel ions in the salt, but it's not going to migrate very far before these come to equilibrium concentrations. So the standard cell potential is 0, but Q is creating the potential, and I think that is so cool. So, anybody can make a battery. You just go pick up a piece of metal, and if you know the salt that goes with that, then you can make a battery. Okay. This will be helpful on a desert island or something. I don't know. Try to make your blinky light so you can get rescued. Okay, so let's make some batteries. So when we have these reduction potential tables and they're sorted high to low, clockwise pairs of reactions are spontaneous. So I picked this reaction here, this nitric acid one, and I wrote it in the forward direction because that's the higher one. Let's pick a metal down below that goes with it. So I picked iron. So I went down here and picked iron. So we're going to run this one backwards. We're going to run this one forwards. So this arrow goes forward. Let me just erase this arrow and draw the other one backwards. So we're going to make this arrow go backwards. So do you see how that's clockwise in this table? The top one goes to the right, the bottom one goes to the left. Okay, and it kind of sets up this thing like this, is what I'm saying. And when these are sorted high to low, we know that will be spontaneous because I'm going to take 0.96 and I'm going to subtract a negative 44. So subtracting a negative 44 makes it positive, and so I know that I have a positive cell potential. The cool thing about using this table is we don't have to go through the half reaction thing. Like if I just gave you nitric acid and iron and balanced that redox reaction, you have to break them into half reactions and add water and add acid protons and balance the electrons. You remember all of those steps? But if you have the table, that's already done for you. Like this is a balanced half reaction right here. And this is a balanced half reaction. All you got to do is combine them and cancel the things that are alike. So we look at this one and we see it needs 3 electrons, and we look at this one and it produces 2 electrons. So we do need to balance the electrons, but everything else has been done for us when we're using the table. So in the future, like if you're in a hurry and you want to balance a redox reaction on your own, just, I don't know, to settle a bet or something, go find one of these tables and find it in the table and it's balanced for you. Yeah. Just find the 2 pairs of half reactions. You've got to still match up the numbers of electrons. And so 3 times 2 would be 6 electrons, and 2 times 3 would be 6 electrons. So they'll multiply the top one by 2, the bottom one by 3, and notice we don't do anything to the potentials, remember? So whenever we multiply the reaction, we do not multiply those potentials. We leave them as is, because it's a force, not a quantity. And so then we combine everything. So we have 2 nitrates. We have 2 times 4 acid protons, and so that gives us 8 protons and so on. So we do this multiplication through, bring everything down. We have 3 irons here. Okay. We could check everything that balances and check our work there, but again, we started with balanced half reactions. As long as we get the electrons to match, we're good. And so then our cell potential is 0.96 plus 0.44 or 1.40 volts. So it's pretty straightforward in using that table. Now let's say I had this, whatever, I had some iron, I had some nitric acid, I've had a scheme for making this into a battery. I could get it to be the right size of my AA that I want to replace because they're 1.5 volts, but this is 1.4 volts. And that's not fun. I want to replace a 1.5 volt battery. So this is the standard cell. Can I get this voltage up to 1.5 volts? That's when we use Nernst equation. Okay, so the standard cell potential is a bit weak at 1.4 volts when compared to a standard battery. So what value of Q would give me a 1.5 volt battery? So this is how we would set that equation up. Here's the Nernst equation. Notice I have the cell potential that I want. I want the 1.5 volts, and I've got 1.4 volts, which is kind of puny. And so then I just want to figure out what Q would be. I know this is going to be equal to 6 because we did the balancing of the reactions, and the electrons exchanged is 6 moles of electrons exchanged. So I know everything but Q, so I should be able to solve for Q. So here are all the numbers. So I'm going to move this 1.4 over here to be a minus 1.4. Okay. Then I'm going to move this negative sign over, and then I'm going to multiply by 6 and divide by 0.59. So moving the 6 over, I multiply by that difference, so that's where this part came from. Moving the negative sign over, that became this negative sign. And then dividing everything by the 0.59, put that in the denominator. And then that's all on the left side. The log Q is on the right. And so to get rid of the log, I take 10 to both sides. Okay, so then I have Q is equal 10 to that mess that I just made. Okay. And so once I have that number, I calculate it. So I've got a 0.1 voltage difference times 6 divided by 0.059 So I have a negative exponent, so it should be something small, and it's 2.7 times 10 to the minus 41. So that's Q. So that's my answer for this question. What value of Q would give 1.5 volts? Well, goodness gracious, the Q is equal to, let me go back and look at the concentrations. You know, it's the nitric oxide gas, the iron 2+ cation, and so it's quite complicated. I think I have it written down here. Yeah, it's right here. And so this is equal to 2.7 times 10 to the minus 41. I've got one equation and 4 unknowns, right? So there's a whole lot of ways I could make Q equal 10 to the minus 41, okay? The simplest way is to make everything 1 except for a single number, right? So if this is 1, say 1 molar, if this is 1 molar, if this is 1 molar, then this one here, iron concentration cubed is equal to this number. So if I just take the cube root of this number, that concentration of iron would give me a 1.5 volt battery. Okay, so that's pretty cool. This 3 came from the cube root of this number here. So to find the iron concentration. That wasn't asked. I think that's a little stretch for you. I'll ask you to solve for Q, but this Q is a pretty complicated equation. And so if I said, if everything else was 1, what would be the concentration of iron? You should probably be able to do that. But anyway, I just wanted you to know where this number came from. It's assuming everything else is 1. And essentially, I mean, you're going to get 1.5 volts out of this because that's such a small number that it might as well be 0. So if we set this reaction up where I have iron metal and no iron cations, then it's going to give about 1.5 volts when it starts out. So that'd be a decent battery. Okay, so let's do one more problem using the reduction potential. This isn't in your notes, but it's using the same table. A lot of times we have reactions that go to Fe3+ from Fe metal. And I look in the table and I find Fe3+. Hey, there it is. But there's a problem. It goes to Fe2+. And that's not what I'm looking for, right? And then down here I've got Fe solid. This is what I'm looking for, but it's coming from Fe2+. So what's the reduction potential for this reaction that I want? I can still use this table, but I've got to do it in parts. Okay? So I've got Fe3+ aqueous plus an electron gives me Fe2+ aqueous. And the reduction potential for that is plus 0.77 volts. Okay. And then down here, I have Fe2+ aqueous plus 2 electrons gives what I really want, and that is solid iron. And that potential is minus 0.44. I haven't switched any of the reactions, notice, okay? I'm just looking at this table using 2 rows that I'm interested in, and if you'll notice, these Fe2+'s cancel. This right here is the same as this. So if I add these together, I end up with Fe3+ aqueous plus 3 electrons gives me Fe solid, and then I add these potentials together. And so I end up with, let's see, 7 minus 4 is 3, 7 minus 4 is 3, so 0.33, a positive 0.33 volts. Okay. So that's handy. So now I have a new reduction potential that I could use in the tables if I wanted to do a reaction where it went all the way from 3+ down to 0, or from 0 up to 3+. And just, again, showing you how you can use these reactions. You add the reactions, you add the voltages. If you flop one reaction backwards, you flop the sign on the voltage. Okay. And where would this go in the table? Well, it would go right here. It's a 0.33 volt reduction potential, so this reaction should go right here. That one's 0.34, so copper going down to copper solid is 0.34. This one is iron 3+ going down to iron is 0.33. So you could have put that in the table. Okay. I have a talk in town at noon, and so we're going to end early, a little bit early. So if you haven't signed the roster, find it, and I'll see you next time.